and his talk is Shaping Planetary Surfaces with Impacts in Volcanic Processes. David.
Thank you. Okay, that's the topic for one of this afternoon's later sessions, and I'm going to lead that off with a discussion of something I'm calling the Lunar Magnetism Hypothesis, and you can see the cast of characters behind this wild idea. Okay, I'm going to have to take you back in time, earlier in solar system history, and I'm going to walk you backwards in a couple of slides. This is the Earth and the Moon to scale as it is today. This is based on geological reconstructions, the Earth and the Moon as it was about 900 million years ago. This is how the relationship between the Earth and the Moon about 3.9 billion years ago, and what we oftentimes refer to as the period of lunar cataclysm or the late heavy bombardment. The Moon in the sky was nearly 3 times the size that you see it today. But then I want to take you all the way back to 4.5 billion years ago. This is the Moon relative to the Earth. It's 16 times larger in the sky. It's something that we actually don't think of very often. So where I'm going to focus your attention for the rest of the talk is between this time here and this time here. And our colleagues at Goddard in the visualization studio put together a wonderful video that illustrates the evolution of the Moon during this time period. So let's take a look at that. Here is the Moon soon after it formed, 4.5 billion years ago. It's starting to cool off. And about 4.3 billion years ago, there is an immense impact event. And let's put quote marks around that 4.3. We actually don't know that age. This is the South Pole Aitken Basin impact event. We've estimated it to be 4.3, but of course that is one of the great unknowns in lunar science and one of the drivers for future spacecraft missions. A few 100 million years later, we had the basin forming epoch, producing the lunar face as we know it today. Okay, what do we know about the early evolution of the Moon? We know something about it because of the success of Apollo and the Luna missions led by the United States and the Soviet Union. They brought samples back to the Earth that we were able to analyze, and this is the story that's been pieced together from the samples. We have an idea that there was a magma ocean and that the magma ocean crystallized. During that process, denser olivine and pyroxene sank. A northocite floated to the top, forming the white highland crust that we can see from our backyards today. There were magmatic intrusions into the crust over a longer period of time. Basaltic lavas eventually erupted onto the surface, producing the dark Mare surfaces that, again, we can see from our backyards. And impact cratering modified the lunar surface throughout this entire sequence of events. Now, my team, my survey team, has spent an awful lot of time evaluating this by measuring argon-argon radiometric system and impact melt breccias, such as 15445 here, seen in the center of this frame. But my international colleagues from Curtin University and now in Sweden, Stockholm, have been also analyzing magmatic zircons in a variety of Apollo samples and correlating those with additional samples by other colleagues in the community. And what we have plotted here is a graph that correlates all of those analyses. The data represent about 250 zircon grains, mostly from Apollo 14 and 17 sites, but also include about 20 grains from the Apollo 12 mission. You can see that at about 4.36 or 4.3, there's a peak in the Zircon Ages. It's centered around 4.32 billion years ago. These data represent magmatic ages, not shock metamorphic ages, which you oftentimes hear me speak about, so that's important, and thus reflect a magmatic event about 4.36 or 4.3 billion years ago. Now you'll see I've also annotated this with a little cryptic bar. That is the estimate for the SPA impact event that we have derived from a variety of reasoned arguments, some of which I'll say something about in a moment. Okay. This peak is similar to several other ages. I think I've seen Lars Borg wandering around, and he's responsible for a lot of that discussion. This includes an Ur creep average model age of about 4.368 plus or minus 0.029 billion years in the recent paper by Gaffney and Borg. And including an I just said this a moment ago. The latter, I should say, has been interpreted to represent the solidification of the lunar magma ocean, although it's sometimes it's difficult to reconcile that model with ancient lunar zircon ages, some of which are older than that, without a very complicated petrogenetic model. And I think that those are Lars's own words in a couple of his talks. Thus, right now we're wondering, are there any other alternative hypotheses for explaining this magmatic signature? Okay. Now, this actually reminds me of something that I was looking at about 25 years ago. Some of you know I had a good fortune of working with Bill Boynton, is he still here, on the KT boundary issue, and trying to interpret or determine what caused the iridium anomaly that was seen at the KT boundary. And the outcome of that search was the discovery of the Chicxulub impact crater and the linking of that crater to the iridium anomaly at the KT boundary. So, if you will, think of the spike that I'm showing you here as a new iridium anomaly, and we're now trying to understand the event or the events that produced it. Okay, so let's take a little closer look at the Zircon Ages and ask the question, what do they actually represent? And it's important to say that they come from Apollo landing sites spanning a distance of 1,758 kilometers, that is from Apollo 12 to Apollo 17. This is an area of nearly 900,000 square kilometers. It involves impact basin deposits that were excavated from depths up to 60 kilometers, that is by the Imbrium impact event. And so this record that I've been showing you in that graph in previous slides provides represents an extensive sampling of magmatic rocks in the near side crust, and that's important. Okay, at the same time, my collaborators in the international community were pulling together that data. We were looking through NLSI at that time, a parallel set of studies. One of those I want to point to is this paper by Ross Potter and others in Icarus 2012, where a series of hydrocode simulations constrained the size of the South Pole Aitken Basin impact event. The best fit model was 170 kilometer diameter projectile hitting at 10 kilometers per second. Also published in that same year in a paper with our NLSI colleagues with Bill Baki's team, we published a paper in EPSL that looked at the impact crater size distribution on the moon and deduced from that the SPA was produced by a relatively slow-moving impactor before the asteroid belt was dynamically excited in what has been called the lunar cataclysm. Shortly thereafter, we combined that modeling with an evaluation of pseudophile element analyses, again in a collaboration between my NLSI team and Bill Baki's NLSI team, and estimated the age of the SPA impact event to be about 4.3 billion years or slightly older. Okay, so this is the outcome of that. I want to go over it again. That SPA was produced by an impactor this size at a relatively slow velocity at about this time. And as I said, these were completely independent studies. They were going on in parallel. But this is one of the nice things that happens when you go to Rocky Mountain Resorts. We had the LPI sponsored the Lunar Highlands Crust Meeting in Bozeman, Montana. Your mind tends to relax. And suddenly I realized that those ages that we were getting may be tied to these impact events that we were studying in parallel, and that then led to this lunar magmatism hypothesis, which postulates that the SPA impact event may have something to do with that magmatic pulse. Okay, so we went back to the Potter et al. Hydrocode simulations of the SPA impact event. In the original paper, we were focusing all of our attention right here, but we had done a model involving the entire spherical moon, and so we interrogated that data, and by that I mean Ross did, okay, and started calculating the total pressure that you see throughout the entire moon. And I'm just showing you 3 time steps, 12 minutes, 16 minutes, and 17 minutes. And look at these immense deviations in the pressure, basically oscillating at the antipode of the impact event a few minutes after the impact event on what is the near side underneath the magmatically rich Procolarum creep terrain. Okay, this is a movie that shows it in action, and you can see that pressure and stress waves radiate around the moon, beginning with shock waves and then followed by high amplitude surface waves. The high amplitude waves generate antipode displacements of about 1 kilometer. That is, the antipode is simply getting disrupted and fractured and sheared all to pieces. Okay, and you know, this thing is addictive. You can watch it over and over and over again. I'm going to spare you that agony and take you to a still plot. Here, what I've done is I've plotted the delta P rather than simply P to highlight the effects of the impact event. Here is the impact event occurring at 3 minutes afterwards. This is 12 minutes, 16 minutes, 17, 18, 19. So you can see that there are these very large pressure excursions at the antipode, and they come, they go, and they come again. These changes in pressure oftentimes exceed 5 gigapascals. They are far in excess of the 0.25 gigapascals needed to fracture the Galburic anorthosite, according to work by Pete Schultz and David Crawford, following laboratory measurements by Tom Ahrens. So significant damage is anticipated throughout the near side, particularly in the near side upper mantle and crust. Okay, so the nice thing about having an NLSI or Survey grant is that you can bring in a huge amount of diverse expertise, and so we turn to Pat McGovern, who is quite expert in evaluating the extension and contraction of crustal and mantle lithologies and how that allows magma to move about. And so this is a diagram showing magma ascent velocity as a function of depth. The surface is up here, this is down. And what this diagram illustrates is that there are magma velocities, positive magma velocities, that take some material from the upper mantle and put it into the lower crust. In words, magma ascent velocity and the effect of mechanical buoyancy is a function of depth in the crust for a horizontal opening event of a duration of 30 minutes. This is derived right out of the hydrocode simulations. These results indicate magma can rise and produce intrusive horizons in the lower lunar crust. This outcome, I should add, is robust. It's not affected by uncertainties in lunar core size and lunar interior thermal state. That is reasonable uncertainties in those parameters. Okay, so in conclusion, we show that the uranium-lead isotopic system in zircon, which was more resistant to impact resetting than the argon-argon system we've looked at in the past, records a major magmatic epoch on the near side 4.36 to 4.3 billion years ago. We show, as did Schultz and Crawford in an almost forgotten paper in a GSA special paper, that the South Pole Aiken Basin impact event produced stress pulses, large displacements, and strain rates that significantly disturbed the upper mantle and crust in the opposing hemisphere. We show that those dynamic excursions could cause mantle partial melts to rise into the lower crust of the moon. And I want to emphasize this last point. Our lunar magmatism hypothesis is not based on a single string of evidence and or modeling, but rather supported by 3 distinct looks at the problem that mutually support the hypothesis. Now, one of the things I used to forever say when we were having debates about the KT boundary and the cause of the mass extinction event is the best hypotheses are those that are testable hypotheses, and this is a testable hypothesis. A good way to test this hypothesis is to apply a sample return mission that allows us to determine the age of the South Pole Aiken Basin. And with that in mind, I prepared a video. So Ashkan, could you cue the video? And can we turn off the light? this, I might add, is completely with real data produced by LRO. Thank you. I'll take questions on the hypothesis or the mission concept.
Thanks very much, David. We have time for one short question.
Okay. This magmatic event, there should be some impact on the Earth because of the gravitational, is there any occurred that we can look at the mirroring effect on the Earth itself, and then see where and what time? Is there any effort on that?
The answer is there might be, but it'd be very difficult to find. I mean, one of the things that those of us in the planetary sciences appreciate is the moon is in some sense a Rosetta Stone for the early solar system history. It preserves a record of these very ancient processes in exquisite detail, whereas those the geologic evidence for those processes on Earth were largely erased by plate tectonics, volcanism, erosion, and so on. So if you really want to understand this epic of solar system history, you really need to go back to the moon.